Ok, doctora Ana Hansen, es su turno de palabra.
Gracias. Doctora Lucia Capra, del Centro de Geociencias en Turquía de la UNAM, distinguidos participantes. Les doy la más cordial bienvenida a esta séptima RACMI 2021 en línea. Para los que no nos conocen, Interpore es una organización internacional científica independiente sin fines de lucro que fue fundada en el 2008 y que tiene como objetivo el análisis, estudio, difusión de conocimientos para la comprensión, descripción y modelización de sistemas de medios porosos, naturales e industriales. El capítulo México de Interpore quedó formalmente constituido en el 2014 y es la rama de México de esta organización internacional. El CMI está integrado por académicos, industriales, investigadores, estudiantes y otros profesionistas interesados en medios porosos. Y los principales beneficios de formar parte del CMI son facilitar la colaboración entre investigadores industriales, académicos, estudiantes, tanto de México como de otros países. Obtener descuentos en las reuniones nacionales que llamamos RACMI y también las internacionales que organiza Interpore. Tener acceso a cursos en línea y otros recursos en la página web de Interpore y acceder al Interpore Newsletter, donde se publican los avances tecnológicos del momento en el área. Por segundo año consecutivo, la RACMI tiene una duración de 2 días. Queremos pensar que estamos creciendo. Y por primera vez se celebra la RACMI en línea. Este año tenemos además el honor de hospedar la distinguida Conferencia Kimberley-Clark, además de 11 trabajos en la sesión de sistemas energéticos convencionales, 3 trabajos y una magistral sobre sistemas geotérmicos, 2 trabajos sobre sistemas porosos artificiales, 4 sobre sistemas ambientales, 3 sobre otras aplicaciones. Entonces, como ustedes pueden ver, y 4 sobre suelos y acuíferos y 3 carteles. Como ustedes pueden ver, son muy variados los trabajos que tenemos. Todavía nos falta abarcar más temas y pues estamos tratando de ampliar los participantes y las ramas de los participantes que participan. Entonces, muy bienvenidos y damos la palabra a la doctora Lucia Capra para que haga la inauguración de esta reunión. Gracias.
Bueno, buenos días a todos. Muchas gracias a la doctora Ana Hansen, presidenta del Capítulo México, y a todos los distinguidos académicos y estudiantes que nos acompañan el día de hoy. Para mí es muchísimo gusto estar aquí con ustedes para la inauguración de esta séptima edición de la reunión anual del Capítulo México de la Interpore, y creo que algo que considero súper importante del esfuerzo que realizan cada año es que permite reunir una comunidad muy variada entre académicos, especialistas, estudiantes de diferentes instituciones nacionales, lo que fomenta, yo creo, la colaboración interinstitucional y multidisciplinaria. Entonces, esta reunión anual es sin duda la oportunidad de intercambiar ideas, presentar avances y fortalecer colaboraciones, propiciando la formación de nuevos grupos de trabajo que permitan impulsar proyectos novedosos de investigación básica para el desarrollo de modelos originales y nuevas teorías, así como una investigación enfocada a la atención de problemas nacionales, con un particular enfoque, por lo que veo del programa de este año, acerca de recursos naturales, energéticos y sistemas ambientales. Algo que no hay que olvidar y que la misma pandemia nos ha puesto en evidencia es que tenemos que estar preparados ante cualquier acontecimiento, cualquier eventualidad. No podemos pensar que ya hemos estudiado todo. Entonces no podemos enfocar solamente nuestra investigación a resolver problemas a corto plazo. Sino que tenemos que fomentar la investigación básica en diferentes aspectos que cada uno de nosotros considera importante, que requiere ser estudiado. Entonces, con el base al programa de esa séptima edición, se puede apreciar que aún con las condiciones actuales que nos han obligado a cambiar nuestra modalidad de trabajo, ¿no? A ser más creativos y resilientes. No obstante las dificultades, se observa de toda forma que hay una muy nutrida participación de académicos y estudiantes en ese foro. Entonces, les deseo las mejores condiciones técnicas en ese caso para la realización de este evento, que sea un encuentro profícuo que le permita fortalecer colaboraciones y desarrollar proyectos de largo alcance. Entonces, enhorabuena y felicidades a todos.
Muchas gracias, doctora Lucia. Entonces, estamos un poco adelantados, me parece, y podemos esperar un poquito que se conecta el doctor Mohamed Sahimi para la conferencia Kimberley-Clark.
Y bueno, ya que hay tiempo, sé que la idea de organizar aquí en Querétaro esta reunión, ya por las causas que todos sabemos se tuvo que hacer virtual, pero las puertas aquí del Centro de Geociencia y del campus UNAM Juriquilla siguen siendo abiertas para, en caso que quieran volver cuando se den condiciones, volver a organizar el evento aquí con nosotros. Nosotros, Centro de Geociencia, es un centro multidisciplinario en donde hay una parte de académicos estudiantes que trabajan en temas que son seguramente de interés para el capítulo México. Entonces van a ser bienvenidos si en la siguiente reunión quieren organizar aquí su evento y poderlos conocer más de cerca, porque yo creo que a veces nos encerramos en lo que hacemos y no sabemos que hay una comunidad alrededor en la cual podemos interactuar y desarrollar proyectos mucho más interdisciplinarios, ¿no? Entonces creo que por lo menos lo que hemos aprendido de la pandemia es que tenemos que aprovechar de esos medios digitales que abren las puertas a conexiones nacionales e internacionales, ¿no? Ya no tenemos el límite que no tengo el dinero para poder pagarme el boleto de avión, ya puedo acceder a ciertos foros y conocer mejor la comunidad en México y afuera que está desarrollando investigación afín a nosotros, ¿no? Entonces, los felicito que hayan podido organizar el evento virtual, porque no hay que dejar de hacer esas cosas, ¿no? Claro, es diferente sentarse a tomar un café y discutir sobre dónde conseguimos recursos para hacer un cierto proyecto y hacerlo así en la pantalla de manera más impersonal, ¿no? Pero tenemos que aprovechar y lo mejor que podemos, los medios de comunicación que tenemos y seguir adelante. Voy a tratar de estar conectado un poco con ustedes para conocerlos más. Es gracias a Sandra que conocí a su organización y ya después tendré que pasar a otros compromisos institucionales. Muchas gracias.
Pues yo acabo de mandar al doctor Mohamed Sahimi el link otra vez. Para él son 2 horas antes, es un poco temprano en Los Ángeles, pero en breve él estará con nosotros. Hemos estado en contacto los últimos días. Isaac, ¿no quieres aprovechar para hablar un poco de la dinámica de la reunión?
Sí, doctora. La dinámica va a ser seguir el programa que teníamos planteado, que todo el mundo tiene. Pido a los moderadores que se ajusten lo máximo posible a tiempo y será una sesión de preguntas, os da una sesión de exposición y una sesión de preguntas. La sesión de preguntas, cada moderador la puede gestionar como entienda. Quiero decir, puede hacer una selección por el chat o puede dar la palabra a quien él corresponda, ¿no? A quien él quiera. Y simplemente eso.
Las preguntas, Isaac, ¿cómo se
Sí.
pueden manejar las preguntas y respuestas?
Sí, yo entiendo que hay dos vías para preguntar, ¿no? Una es por el chat y el moderador elige la pregunta o las preguntas que el moderador considere, o directamente el moderador puede dar la palabra a un miembro y que lance la pregunta en vía oral, o mezclar las dos partes, hacer unas preguntas que estén en el chat o hacer algunas preguntas que ya directamente están en oral, no sé. Se puede hacer ya dentro de cada sesión, cada moderador tendrá la libertad de exponerlo como él entienda. Disculpe, el doctor Mohamed Sahimi es la persona que pone Irán, ¿no? Disculpe,
Sí.
doctor.
Welcome, Dr. Sahimi. You are mute.
Okay. Good morning. I'm here.
Welcome. So I will present you, Dr. Sahimi, and then we can hear your conference.
Should I start now?
No, I will first present you, but I will do that in Spanish.
Okay, all right.
Okay. Gracias. Mohamed Sahimi es profesor en Ingeniería Química y Ciencias de Materiales y es chair de NIOC, que es la compañía de petróleo en Irán, en Ingeniería Petrolera en la Universidad del Sur de California en Los Ángeles. El profesor Sahimi obtuvo su licenciatura en la Universidad de Teherán en 1977 y su doctorado en la Universidad de Minnesota en 1984, ambos en Ingeniería Química. Desde 1984, el doctor Sahimi labora en la Universidad del Sur de California y fue jefe de departamento de 99 a 2005. Sus intereses de investigación incluyen flujo, transporte, reacción, absorción, deformación de medios porosos, caracterización de redes de fracturas en rocas, transporte de mezclas de fluidos en membranas y transporte de fluidos y macromoléculas en materiales nanoestructurados. Ha publicado más de 400 artículos y 4 libros y ha recibido varios reconocimientos por su enseñanza e investigación, incluyendo el premio de miembro vitalicio honorario de Interpore. Damos la más cordial bienvenida al Dr. Sahimi, quien presenta el trabajo Medios porosos, pequeños y grandes, desde el modelado atomístico de membranas nanoporosas hasta el modelado del flujo y transporte en formaciones geológicas. Dr. Sahimi, we welcome you and we look forward to hear more about porous media, small and large, from atomistic modeling of nanoporous membranes to modeling of flow and transport in geological formations. Please, Dr. Sahimi, will you share your presentation with us?
Good morning. I'm honored and delighted to be here, to be with you. I thank you for for inviting me to talk today. And as you mentioned, I'm going to talk about some porous media materials at various scales from small to large. When the porous material are very small at the, let's say, nano scale, then we need to do molecular modeling. And then when at the lab scale, then we do another type of modeling. And then when we go to larger scale, for example, oil and gas reservoirs or groundwater aquifers and so on, we do another type of modeling. And of course, we all know, most of us, if not all of us, have worked on various types of porous media. At the largest scale, as I mentioned, we have oil, gas, and geothermal reservoir. We have aquifers, and we also have landfills, because landfills, when we store the trashes, are actually porous media, and in many ways are in fact more complicated than, let's say, oil and gas reservoir, because in landfills we have biodegradation, and therefore we have all sorts of nonlinear reactions that happen underground. Then we have intermediate scales, which are, for example, adsorbent packed below particles, gas storage material, and so on. Then we have a smaller scale, for example, catalysts, membranes, wood, pavement, brick, papers on which we write and print, label papers that we put on our windows or our cars or so on. And then if you look at the literature right now, we will see that there is a lot of work that has been done in nanotubes. For example, people look at protein aggregation in small pores in order to mimic the crowded structure of cellular material, or diffusion and reaction in biological tissues. But they all actually benefit from knowledge of porous media, because these materials, biological materials, in some sense represent porous media. So knowledge in porous media community can be transferred to this type of system as well. Of course, people have studied single and two and three phase flow in porous media, and the rheology of the fluids have been both Newtonian and non-Newtonian. People have looked at, including myself, diffusion, dispersion, reaction, adsorption, and deactivation, which occurs in catalysts. When the catalyst dies, we call it deactivated. Of course, people use membranes to separate fluid mixture, whether it's gaseous or liquid. In filters, as well as formation damage in old reservoir, we have clogging of porous media. We have deformation, of course, and swelling in a variety of porous media. For example, when you inject CO2.
Dr. Sahimi, excuse me, are you going to share your presentation?
Am I going to what?
Share your presentation.
I've been talking for 5 minutes. You don't see it?
No, I thought you had an introduction but no presentation.
I have been talking for 5 minutes.
Yeah, I know. I've been talking for 5 minutes.
Yeah. All right. Can you see it now?
Yes. Yes, Dr. Sahimi.
Okay. I apologize, because I thought everybody is seeing it.
Yeah.
All right. So I start from scratch again. Okay. Quickly, the world around us is full of porous media and materials. At the largest scale, of course, we have geomaterials, oil, gas, geothermal reservoir, groundwater aquifers, and so on. At intermediate scales, we have adsorbents, packed bed reactors, porous material that people use for gas storage. And at lab or a smaller scale, then we have catalysts, membranes, wood, pavements, bricks, print papers, label papers, and so on. And in fact, if you look at the literature, nowadays, one of the problems that we are looking at is flow and transport in very confined media, such as nanotubes, or biological phenomena, such as protein aggregation in confined cellular materials. But even these type of problems benefit from experience and knowledge in porous media, simply because these, for example, biological tissues represent some sort of porous media. Many phenomena have been studied and have been involved in some of them. For example, single and two-phase flow. The fluid could be Newtonian or non-Newtonian. We have been studying a lot of people, diffusion, dispersion, reaction, absorption in porous media. And then the activation, which happens in catalyst particles when the active side of the catalyst is covered by coke and other undesirable reaction products. Of course, people use membranes to separate fluid mixture. We have formation damage in old reservoirs, for example, when we inject water into the system. And we also have filters which give rise to clogging of porous media. Of course, a lot of porous materials swell and deform as a result of doing something to them, either mechanical or physical chemical. For example, when you inject CO2 into a spent oil reservoir in order to store it and sequester it, often the porous medium swells as a result of injecting CO2. Of course, people look at wave propagation because like seismic wave, for example, which could be acoustic or elastic. And of course, propagation of fractures in rock and the resulting earthquake has always been a problem of interest for decades. Now, of course, we have a huge disparity between various scales in which porous media are involved. At the most fundamental level, we have quantum mechanical calculation to the left of the diagram. And there, people use ab initio or density functional theory to calculate electronic structure of atoms. But of course, that's very small, and also computational power does not allow us to simulate large systems. Then people go to one step further at a little larger scale. They use molecular dynamics simulation, MD simulation, and use empirical or semi-empirical force field, which I describe in a couple of minutes. Then we go to meso scale when we have pores and grains, and then we do larger scale when we use finite difference, finite volume, finite element, and so on, with computational degrees. And then finally we go to field scale porous media, where we have to upscale from a smaller scale to larger scale in order to say something meaningful about our porous media. And as you can see, the scale goes from angstrom at the smallest level to kilometers at the larger scale. So there are orders and orders of magnitude difference between these type of porous materials. So then the question is, what type of models people use for modeling porous media? One type is what we call reconstruction at the smaller scale, which is quantum mechanical and molecular dynamics simulation. Then we can use molecular pore networks. Then we can use percolation model. Percolation, if you're not familiar with it, is a model basically on lattices on networks that quantifies the effect of connectivity of the pores on the overall properties of porous media. Then we have pore networks, which are basically like percolation model, but they don't have to be percolation model. These pore networks could be hypothetical, it could be abstract, but now we also have techniques to extract them from images of porous material, and therefore they are very accurate. We could also use directly two-dimensional or three-dimensional images of porous media and do modeling computation with those images. This is becoming more and more common because computational power has increased dramatically. We could also do reconstruction at larger scale, where people use geostatistical modeling. And then, as I mentioned in the last slide, we use upscaling in order to go from intermediate scale to the largest scale. So since I mentioned reconstruction, let me pose the question: what is this reconstruction? Because I'm going to talk about it in a minute. And reconstruction, by definition, is suppose that I have a limited amount of data for a porous medium or porous material. My goal is to use that limited amount of data to develop a model or realization of that porous media, because reconstruction is often stochastic, and therefore you can generate many realizations of it, such that that model that I develop based on that limited amount of data not only honors the data, in other words, they satisfy the data exactly, but they are accurate enough to provide accurate predictions for other properties, in particular for those properties for which we didn't use any data in the reconstruction. Reconstruction can be done at various length scale, and there are many reconstruction methods. If you look at literature, and in fact, I'm writing an extensive review of all these methods that hopefully will be published this year. Let me just, after this introduction, let me just talk about 3 problems. Each problem I describe relatively briefly. I cannot go into great details because each of them is a talk by itself. But let me talk about reconstruction at a smaller scale, when we use quantum mechanical and atomistic modeling of membrane for a problem that we have been working on for many years. Then I go to the opposite scale, reconstruction at larger scale, where we do reconstruction of fieldless scale porous media and do flow simulation. And then the third problem, which is very interesting, is absorption and swelling of porous material. There is also a fourth problem that I don't discuss it. I have worked on it for many years, and that's a unified approach to analyze data, upscaling model of porous media, and simulating multi-phase flow in geological formation, for which we use 2 types of relatively new transformation. One is wavelet transformation, and one is curvature transformation. If you want to look at the references for the fourth problem that I won't discuss, I give a reference at the bottom of the page, a paper that was published in Transport in Porous Media about a couple years ago. All right, so let's look at problem number 1, which is reconstruction at the smallest scale. The problem that I discussed is the following. People have talked about hydrogen economy, so use hydrogen as a source for energy. But the interesting thing about hydrogen is that although hydrogen is the most abundant element in entire universe, in fact, as we all know, fuel for stars is basically hydrogen, which are fused together, converted to helium and heavier atoms, and that generates energy. But on Earth, if you want hydrogen, we have to produce it. It's not, we don't often find free hydrogen. So the way they do it is by steam reforming. So what it means is that, as I show in the figure, we, for example, take methane and water, put it into a reactor, a steam reforming, and they react and produce hydrogen with other gases. It also, for example, it generates hydrogen and CO2. Now you need to separate hydrogen from CO2. The reaction takes place at high temperature. It's about 800 degrees centigrade. And also the reactor is sort of, obviously, for example, methane that we put in is not pure, it has other gases. So the environment for the reaction has many gases, and also it could be corrosive and sort of poisonous. So what we want to do is develop a polymer, a membrane, to get the hydrogen separated from the other gases that come out of the reactor. We have developed this membrane. Since the temperature is high, we cannot use low temperature membranes such as, for example, polymers or carbon membranes or carbon molecular sieve membrane. We need a membrane that can resist reaction, is basically non-reactive, and can resist high temperature and has a strong mechanical resistance. For that, we have developed silicon carbide membrane, The way it's done is that we have a membrane support, which is also silicon carbide, except that the pores are too large for separation. Then we deep coat the membrane into a solution of a polymer. Then the polymer undergoes pyrolysis. It loses many atoms that it has, and at the end it generates a membrane layer, which is basically silicon and carbon. And you see it on the right side. The bottom part of the figure is the porous support, and the top layer is the membrane. The membrane has worked. It has good performance. We published 2 papers about 12 years ago, showed that it has very high properties for separation, but the performance wasn't optimal in the sense that it does have good separation factor, about 100 to 100 separation factor, which means that for let's say if it's 100, that means for let's say for 100 molecules that leave, one of them is another gas, and 99 of them are hydrogen. But the flux is low, and that's not practicable at practical scale, because a good membrane should be relatively thin, should be strong, and should have high flux, and of course separation. In order to optimize the performance of the performance of the membrane, we needed to develop a basic molecular scale of the membrane, so that we get some control on what type of factors affect the structure and performance, and therefore use that in order to optimize the performance of the membrane. Since as I mentioned, the membrane is made by pyrolysis of the polymeric layer at the top of the membrane support, and there are all sorts of reactions that happen during the pyrolysis. We need, if you want to do molecular simulation, we need atomistic models that are basically simulated by reactive force field. Force fields are basically equations, for those of you who may not be familiar, that describe interatomic interactions between atoms. And ordinary forces are not reactive. In other words, they don't allow for automatic reaction if there is any reaction. And you have to manually tell them that if this thing happened, then there is a reaction and let's say a bond formation. But there is also reactive force field that automatically allows for reaction and formation of bonds to take place, and those are rare and those are computationally expensive. So we have 5 stages, 4+1, I always say, of developing this model. The first model is to develop the reactive force field, as I mentioned. As soon as we have the reactive force field, which I describe how we do it, then we generate the model of the polymer. Then we use the reactive force field and simulate pyrolysis of the polymer. At the end, we get the silicon carbide, amorphous silicon carbide membrane. Then we simulate transport of gas mixture in the model, and then we see whether it is accurate, it agrees with the experiment. And if it is, then we start playing around with the parameter of the model in order to optimize the performance of the membrane. Now, as I said, the construction needs original data. And in this case, the original data comes from 2 sources. One is, of course, experimental data on pyrolysis, because when the pyrolysis takes place, we know what leaves the system. We can measure them. Therefore, if our model is accurate, it should agree with reaction product that the experiment indicates. But at the most fundamental level, we need data for development of the reactive force field, and that is obtained by quantum mechanical calculation. In order to develop the force field, as I said, force fields are basically equations that express the total energy of the system. So, for example, if you look at any molecule, there are bonds between two atoms, and therefore, if you deform it, it would cost some energy to do it, to stretch it or compress it. So the first term on the right side is bond, and of course, it's between two atoms, so it's a two-body interaction. We also have van der Waals reaction that we are all familiar with it. A lot of these atoms, all of these atoms are charged, and therefore we have Coulombic interaction between them. These are all two-body interaction. Then we have three-body interaction when, for example, we have one central atom and two other atoms, and there are bonds between the two other atoms and the central atom, and therefore we have two bonds connected at the same atom. So that's three-body interaction. Then we have four-body interaction. For example, three atoms are in one plane, a fourth atom is out of the plane. So that's four-body interaction. And we also have excess energy, which we call it over and under, which means that, for example, a pure silicon carbide should have a coordination number of 4. In other words, every atom, carbon or silicon, should be connected to 4 other atoms. But since this is basically a process that you go over it, it could be that you develop some defects so that the coordination number is larger or smaller than it should be. And of course, this is a multi-body interaction, so we have to account for it. So what we do is we parameterize this expression, and there are a huge number of parameters. The number of parameters are 438 actually. And then we estimate most of these parameters by quantum mechanical calculation. The way we do it is we take a general polymer, that the polymer that we actually use, which is hydroxypolycarbonxylene, HPCS, belong to that family. We take a small pieces of that polymer, let's say a few hundred atoms from that polymer, for which quantum mechanical calculation is feasible. So we do that, and then we try to adjust, and we get some data with quantum mechanical calculation. And of course, those data are exact because we are doing it at quantum mechanical calculation using density functional theory. And then we adjust the parameters of the force field in such a way that when we calculate the same properties with the force field, molecular dynamics simulation, it reproduces the same thing. So that's basically adjusting your parameters in order to honor the quantum mechanical calculation data. And these are all described in 4 papers that we published over the past few years. Then at the end, what we get, we go through the simulation of pyrolysis, and then we get at the end final structure of silicon carbide, and which is what I show here. Then we want to test it to see whether this is actually an accurate structure. One way is, for example, to look at the coordination number, Z, and for those of you who are familiar with it, is computed from the radial distribution function G of R, which is basically the probability of looking at a structure and probability of fixing a distance R for one atom and looking at where are other atoms. When we calculate for this structure, the coordination number turned out to be 3.6. But as I said, pure silicon carbide has a coordination number of 4. So what it means is that some of these silicon and carbon may have double bonds, and there might be also some impurity. So how do we know that the overall structure is correct? Well, we calculate the radial distribution function, as I showed you, that we use to estimate the coordination number. The computed one is at top left. As you can see, we have carbon-carbon atoms, bonds, silicon-silicon bonds, and we also have silicon-carbon bonds. Now, at the bottom on the left, you see experimental data for the same silicon carbide. And again, you can see that it shows silicon carbide silicon-carbon bond, silicon-silicon, and carbon-carbon. And the most important thing is the location of these peaks. For example, we have one peak for CC in the computed structure, and we have one for CC for the measured structure. And as you can see, they are at the same distance R. In other words, that produces the correct structure. The other thing that we calculate is X-ray diffraction pattern. On the top, we see the computed structure. At the bottom, we see the experimental data. Again, if you look at the location of the peaks, it indicates where these atoms are and so on. They actually quite nicely. And therefore, we know that this structure is very accurate as far as silicon carbide is concerned. So that was one problem. And then we did computation for this. And then we simulated transport of CO2, CH4, and hydrogen through it, which is what we use in experiment. And since the experimental data, at least at the qualitative level, and in particular for separation factor, agree with it, then we started doing simulation at larger and larger scale. Because remember, the thickness of this material that we produce in this simulation is very small, because we cannot do huge simulation. But we can do several size structure and then extrapolate to the typical size that we want, and then ask ourselves, if I want to have this separation factor, let's say 50 or 75 or 100, what should be the thickness of the membrane? And in this way, we estimate the thickness. And in fact, when we did the experiment, it more or less agreed with the experiment. So that means that we now have a model that not only honors data, it also produces good predictions for other types of properties, and also can be used for optimizing the performance of the membrane. So that was problem number one at the smaller scale. Now let's look at larger scale, let's say groundwater aquifers or oil and gas reservoir. And of course, there we can no longer use molecular dynamics simulations, simply because it's not feasible. Even a smallest piece of material has millions and zillions of atoms. So obviously, when you go to a large scale structure like an oil reservoir, there is no way you can do it at atomic scale. So what we need to do is to reconstruct it, but not by atomistic calculation, but by other methods. People have developed all sorts of methods for it in order to reconstruct it. Typically, what they do is they define an energy functional, which is basically the difference between data and the prediction by the model, and they try to minimize it so that the predictions and the data agree with each other. And the way they minimize it is, for example, by one of these optimization methods, such as simulated annealing or genetic algorithm or other methods. In the past, people used two-point data. In other words, when you look at, let's say, a piece of material at position U, then you look at the statistical properties of that material at the position U plus H. And by varying H, you get some information about the structure of the system. But although that produces some reasonable model for some properties, it is not always very accurate. In fact, in most of the time, when you go to three-dimensional system, it's not very accurate. So what people did was they went to multi-point distribution. In other words, not only you look at a point at U and a point at U plus H, but you also look at a point at U plus H1 plus H2 plus H3 plus H4, so that you get a sense of what's going on around this whole system. Originally developed by geoscientists, Arpad, Zhang, Strebel, and so on, my group developed a new approach, which we call it cross-correlation function simulation by my former graduate student, Pejman Tahmasari, and myself. I list here 3 papers, the original papers. Since then, we have published many other papers, but the 3 original papers were published in 2012 and 2013. The work is still continuing. We are looking at other aspects of it. So how does this work? Well, let's say that we have some data, and this data, for example, is in terms of an image of the system, which we call the training image. So what we do is we want to develop the model. So what we do is, whether we want to have a two-dimensional model or three-dimensional model, we represent it by a computational algorithm in 2D or 3D. Then we partition it into blocks, of course. And then what we do is between the blocks, we also have a small overlap region. The overlap region plays a fundamental role here because it allows sort of a smooth transition from one block to another, and it doesn't generate artificial features that do not exist in the data. For example, cracks that don't exist, or mismatches that don't exist, and so on. Then we reconstruct the model. In other words, we set up the computational grid populated by heterogeneity of the data, block by block, and we do it around one-dimensional raster path. For example, we go vertical and then come back. Once we reach the top of the system, we come back to the next row and start from bottom and then go up. Or we can do it horizontally, we can do it vertically, we can do it diagonally, or we can do it in a random orientation. It doesn't matter, but we do it one by one. Then what we do is we sample the digital image, the image that we have, or the data that we have, and we, using that sample, we fill out the first block of the computational grid or model that we want, and also the overlap. Then the overlap, we call the overlap data event, because we put this data in the overlap, but if it doesn't satisfy the requirement that we want, we remove it and we put some other sample data. So that's what we call it event, because this event can change. Then we match overlap region with the entire set of data that we have. Let me tell you how it's actually done mathematically and computationally. Let's say that your digital image is DI, and your event data in the overlap region is DEVT that I have it. Obviously, we want to minimize the difference between the two. In other words, we want to have as minimum a difference between the model and the data as possible. So what it means is that we have to minimize that expression. It's basically a Euclidean distance between the data and the sample of data that we have put in the system. If we expand the top equation, then we get the second equation. Now, if you look at the second equation, the first term on the right side is always positive. The last term on the right side is always positive. And therefore, if we want to minimize the Euclidean distance, we have to maximize the term at the center. But the term at the center, if you look at it, is basically a cross-correlation function or a convolution between the image, between the data and the sample that you have taken. And that's what we call at the bottom the cross-correlation function. It is nothing but a convolution between the data that you have and the sample that you have taken. So what it means is that you want to maximize this, or if you work with the inverse of it, you want to minimize the inverse of it. All right, so that's basically the way it's done. This is, let's say, the system. This is initial computational grid. So you take one sample from it, we insert it there. Then this is overlap region with it, and then you put the next block in it. You take another sample, you put there. Then you continue this until the first row of blocks is completed. Then you go to the next row. Then you take another sample, and you put it in, and you continue it, taking sample. And for example, here, the raster path is horizontal. In other words, you start from bottom left corner, you go all the way to the rightmost part, and then you go to the next row, and so on and so forth. And then at the end, you hope that you get a structure like this. But of course, you have to maximize the cross-correlation function or minimize the inverse of it. So that means that you take many samples and you check what the correlation function is. And therefore, you have an ensemble of these plausible realizations, but one of them has the lowest possible inverse of correlation function or maximum cross-correlation function. And that's one plausible realization that you have for this. For example, here we have a digital image on the left. It is 1,000 by 1,000 in 4.8 CPU seconds. we can produce several realization of it, then another one, and another one. This is one type, this is another one, and that's a third type, which is very large, three-dimensional large, and in less than a CPU minute, we can generate accurate realization. Of course, we have to check to test to see whether these realizations are accurate, and we do that. For example, here we generate a fracture pattern. It's very large, 300 by 300 by 10. It contains 900,000 cells. These are actual data that provided to us by a Japanese oil company, and we reconstructed at very large scale in about, let's see, it's about, it has 4.5 million cells that we generated in very only 7 seconds, and this is a view of another view of the same system. As I said, we have to test whether to see whether these are accurate or not. So what we do is we, for example, calculate variograms in the horizontal direction and y direction. But most importantly, we calculate the multiple point connectivity function, which I show at the bottom, which is probably, for example, let's say that you ask yourself, what is the probability that if I take 100 points from this realization that I have made, all these 100 points are in the pore phase, not in the matrix phase. In other words, all these 900 points are connected through the pores. This is a tough test because 2 points is easy to match, 3 points is easy to match. But multiple points, where the number of points that are connected is large, is difficult to match unless your method is accurate. And the previous method that I mentioned failed this criterion, whereas the method we have developed agrees very nicely. And here we show that, for example, from connectivity from east to west, for example, the black line is what we calculate from the image itself, so that's basically exact data. And then the gray ones are the same probability calculated for several realizations. So you can see all the realizations fall very, very close to the actual data. So that means the connectivity satisfied. So for example, here we have several, 3 of them from the original, and then it's satisfied. But then after that, we decided to refine it so that it can do other things. For example, if the porous media are very, very heterogeneous, then the method might develop some discontinuity between blocks. And then in order to remove those artificial discontinuity, we use graph theories to address that. We also use it for granular material, which means unconsolidated porous media. And also, we have also, most importantly, which is a very difficult problem, we have extended the method to reconstruct non-stationary porous media, because the assumption in these reconstruction method has always been that these are stationary porous media. In other words, if you calculate probability distribution function for any property of the system and you go throughout the space of the system, the probability distribution function doesn't change. It remains the same thing. But non-stationary porous media, and in fact, large-scale porous media are often non-stationary, they're not stationary, as evidenced by a variety of data, are non-stationary, and therefore you need to be able to reconstruct such methods also. And we have published a whole bunch of papers here that I give the references here. All right, so we have developed that. So let me now talk about the final problem, which is problem of swelling and deformation of porous media and materials. Of course, we all know that swelling and deformation happens in every problem that we might encounter. For example, in biological tissue, red blood cells swell and deform. In polymer network, we all know that polymer networks are used drug delivery system, medical, lots of materials, plastic, and so on. If they absorb, for example, liquids or gases, they swell. In geomaterials, for example, we know soil, rock, and concrete, they deform. In filtration process, we have chemical, biological materials from processed liquids. I mentioned at the beginning of my talk that CO2 storage often leads to soiling of the system. And of course, in coal seams, that has a large amount of methane. And in shales, we also have deformation. And one particular type of material that is becoming very, very popular is called metal organic frameworks, or MOFs, that people use for gas storage, because the problem of gas storage is a very important problem for future energy resources. And we developed a model for this that couples the deformation of the system with the fluid content of the system. Basically, we write an expression for the energy. For the fluid energy, we have two first terms, three terms, sorry. Let me put this here. We have three terms. I write it on the top equation. One is the fluid itself, the first term. The second term is the interaction between the fluid itself. And then we have the external chemical potential or pressure that is applied as a result of, for example, injecting liquid or gas into the system. Then, of course, the solid skeleton of the material also deforms, and therefore we have an expression, the second line equation, for the elastic energy of the skeleton of the material, which is basically a standard linear elasticity. But of course, we can also use nonlinear elasticity if it's necessary, because it only changes the expression for the total energy. And then we have coupling between the fluid that goes into the material in order to soil it up, and the solid skeleton, which is basically has two terms. One is due to wetting, the top expression on the third line on the right side, and then between the compressibility or interaction between the fluid and the solid. Of course, in statistical mechanics, we know that if we want to obtain the equilibrium structure after the fluid has been introduced into the material, what we do is we minimize the total energy, just like we do in molecular dynamics. We minimize the energy. We have two variables here. One is the displacement of various points of the system, and one is the density of the fluid that we have put into the system. So we have to minimize the energy with respect to both of them. And if we do that, then we get two equations. One is for density field, and one is for displacement field. So as you can see, the two equations are coupled. These expressions have parameters. For example, we have here epsilon fs or lambda I or epsilon ff, and so on. All of these parameters, in fact, can be calculated by molecular dynamics simulation. So, or if you want to do it faster, you can feed it to some experimental data. We have done both, and in both cases, it produces very accurate results. So that means that you have to solve these coupled equations, one for density field, one for displacement field. And then, let's see if I put it here. Once we do that, then of course we know where the fluid is, we know where the solid is, and how much it has deformed. And then we can calculate, for example, the absorption isotherm, and so on. And the first paper that we published in this area was back in 2017 in International Journal of Greenhouse Gas Control. But let me just focus this part of the talk on a particular type of material that I mentioned, and these are metal organic frame or MOFs, and they are very popular methods. They are nanoporous materials and have many applications in separation, catalysis, and in particular for gas storage, because they have large capacity for storage of gases. They have many unique characteristics, which is why they have become very popular. First of all, they have large surface area, which we always desire. their porosity is tunable. It can be changed. And most importantly and most interestingly, they undergo deformation which is reversible. In other words, they, for example, expand and then they also contract and compress. Here on the right, at the bottom, I show various applications that they have in sensor, drug storage, gas storage, separation, purification, catalysis, and so on. Now, I should mention that theoretically speaking, MOFs are not one unique material. Theoretically speaking, there are thousands of MOFs that you can make. They have all sorts of structures. I'll show some of them here. And in fact, people have developed very nice computational algorithm that can compute some of these properties, for example, for gas storage, in order to decide which one has the largest capacity for gas storage. There is a structural transition that is called breathing, and in particular, one type of MOFs, which we call MIL 53 or MIL 53, which is due to the institute where it was made in France. It undergoes a structural transition. What is a structural transition? It is the transition between large pores and narrow pores. So for example, here, this is the structure. Then it expands a large pore, it forms like this. And then if you release the external factor that caused this expansion, then we'll go back to the narrow pore. And this phenomenon going from here to here is called breathing. So it's just like we take a breath and then our lung expands and then we release it and then our lung contracts. So this is basically a breathing phenomenon. And this is a very important property of this because, as I said, one desirable feature of this material is that it undergoes reversible deformation. So it goes from to large pores, and at the end it goes back to narrow pores. And if you look at, for example, absorption isotherms, then you see that it, for example, looks like this. It goes from narrow pores to large pores. So this is the structure in nanopores, this is structure in large pores. For example, if you put CO2 in it, if you add CO2 in it, you go to large pores. If you remove CO2 from it, then it goes to narrow pores. So there's a narrow pore to large pore and large pore to narrow pore transition between the two. And I repeat again that this is reversible, which is actually quite good, because that means when you store it, it expands, so it takes more and more CO2 or another gas. And then if you want to release it, you can easily release it and it will go back to its original structure. So we decided to apply the model that I described to you to MOFs. So what we did was we took a three-dimensional image of crystalline structure of the MOF. We discretize it by tetrahedral elements, and then we solve for the coupled equation that describes the density of the gas and the deformation of the structure in the material. At low temperature and pressure, a nanopore phase is most energetically stable form. The isotherm that you will see at low temperature is type 4 of isotherm according to International Association of, the international criteria for absorption isotherm. The first step, we are in the nanopore phase, which is in this area, the lower part of the left side of the curve. And the second step is large pore phase, which is the right side and the upper. And here I show some experimental data for CO2 absorption for these MIL structure, as well as absorption isotherm for CH4 at various temperatures. So we computed the same thing for this at the same temperature for CO2 at 343, for which we have experimental data, and for methane at 250. And at these at the high temperature, the absorption isotherm is type 1. And here, for example, we have for CO2 absorption, here we have for CH4 absorption. And these actually agree very, very nicely with the previous data that I showed you here, not only in terms of the shape, but also in terms of the numbers. This is the absorption isotherm, but of course, this is a model for deformation also. So we can calculate the strain versus pressure, the pressure of the gas that is coming in, or the pressure is generated in the internal structure. And of course, if a strain is negative, then that means that the material is contracting. And if a strain is positive, that means the material is expanding. And as you can see, the model predicts both of them, a negative strain and positive strain corresponding to contraction and expansion. This is for CO2, this is for CH4, and it indicates that the material undergoes large structural deformation as a result of CO2 absorption and CH4. The details of the model and computation and everything was published in a paper in Journal of Physical Chemistry, about a couple of years ago. Okay, so these were the three problems that I discussed. One is at the smallest structure, at the atomistic structure for membranes, one type of porous material, which was a reconstruction. The other type was the opposite scale, which was at the field scale that we generate for example, oil, gas, geothermal reservoirs and shales, for example. And then in between is MOF structures that are sort of mesostructures. And we develop model for absorption and deformation of gases and liquids into this type of material. So as you can see, there is a wide variety of approach to these porous materials, and the right approach that we want to take is the approach that suits best the type of material that we have. Of course, if you could do atomistic first principle calculation for any type of porous material, that would be great, but it is impossible, and I don't think it will ever be feasible to do it for large scale porous material. So we need to develop other models, and I describe a few of them here. And of course, a lot of people have been working on this type of material and have done excellent work on this. And if you, for example, look at my own papers, we'll see that we credit all of those. They have done great work. Okay, at the end, I need to acknowledge that, of course, none of this work can be done. Those of us who are in an academic setting, we know that we need to have doctoral students, good doctoral students, in order to do this. The membrane work was PhD work of Saber Nasserivar, a PhD student who's at Caltech now. The reconstruction at large scale was done by Pejman Tahmasebi, who is now a faculty at the University of Wyoming. And the third work on MOFs was done by Sarah, who is at the University of Texas at Austin. In this, I have had collaboration with my colleagues. Theo Satsis and I have had collaboration for over 25 years. He leads the experimental component of the work for membranes, for example. And then in atomistic simulation, we also collaborated with Professor Bill Goddard of Caltech, which helped us to develop the reactive forcing. So with that, I thank you for listening to my long talk, and I will be more than happy to answer any question if I can answer.
Thank you very much, Dr. Sahimi, for this very broad and at the same time very precise insight in porous media characterization and modeling. You give excellent examples on how the same theories can be used for different applications. And we have one question here.
Yes.
I'm going to read it to you. Thank you, Dr. Mohammed, for your excellent presentation. This question is from Rodolfo Camacho.
Yes.
Could you please comment on the order reduction techniques to address the model scaling problem?
Could you repeat the question again?
If you can comment about the order reduction technique to address the model scaling problem.
Order reduction?
I think maybe Rodolfo, you can open your microphone and ask and specify more your question.
I don't understand the precise questions. You mean, did Dr. Camacho said order reduction? Is that what he said?
Yes, that's correct.
What do you mean by order reduction? You mean removing degrees of freedom, or what is it meant by order reduction?
Rodolfo, what do you mean with order reduction? Rodolfo Camacho? Maybe he's, let's see. Isaac, we need to unmute Rodolfo Camacho's microphone, please. Isaac, ¿puedes por favor activar el micrófono de Rodolfo Camacho?
Ya está, doctora.
Gracias.
Yes, my question is related to the how to capture through this technique of order reduction, how to capture the main characteristics of the physical aspects of one scale, especially going from smaller scales to larger scales. You need to use some mathematical tools called order reduction. I think.
You mean, I believe you mean upscaling, how we go from a smaller scale to larger scale.
No, yes, especially in the modeling.
Yes. As you saw, for example, in the membrane problem, we did upscaling in the sense that we went from the smaller scale, which is atomistic electronic structure calculation. We got some data, and then we trained our force field in order to mimic that data, and then we use that to simulate the system at larger scale, because the quantum mechanical calculation was with only a few hundred atoms, whereas the molecular dynamics simulation was for tens of thousands of atoms. So we trained the force field to mimic the smallest structure, and then we use it to go to larger structure. And then from molecular dynamics, you can, for example, get various things like effective diffusivity, separation factor, and so on. Now, if you want to go to larger scale, larger than molecular dynamics, then you set up pore network models. Pore network models for, let's say, a membrane. Now, in pore network models, of course, at the pore scale, you need diffusivity, you need rate of transport, and so on, which you calculate from molecular dynamics simulation and put it in the pore network model, which could be very, very large. In pore network model, of course, you don't have interaction force like in molecular dynamics at meso scale, but it takes the input from the molecular dynamics in order to do pore network calculation. Now, if you want to still go to higher scale, then let's say, for example, you have you want to do a finite element calculation at larger scale. Then obviously a finite element or finite difference, for example, every block of that computational grid is a small porous medium by itself. So it needs effective properties. So that means you use pore network calculation to calculate those effective properties, let's say effective permeability and so on, and you put it in your finite difference grid at larger scale. So you go from a smaller scale, smallest scale to next scale to the next scale, and so on. Mathematically, of course, people do multi-scale, averaging, which is a very difficult problem. But at the end, when you develop some sort of working equation, when you do multi-scaling, upscaling, then you will still have to discretize those equations and solve them numerically. So at the end, you will still have to come back to numerical calculation. I hope I did answer your question.
Yes, sir. Thank you for your explanation. Yes, of course, the homogenization, the averaging technique that you are mentioning is an alternative. But,
Yes.
For this ordered reduction is kind of a more mathematical way to proceed with this upscaling process. But thank you for your explanation, and I give the space for some other people that want to have some questions for you.
Sure.
Thank you, sir. Thank you.
Let me mention that if you have any question about my presentation, you can send me an email, and I'll be more than happy to discuss it over email. And if you want, I can send you some of my papers or point you to other papers that people have done, because as I said, a lot of people have done a lot of good work. I only talked about my own work, but a lot of people have done excellent work in this area.
Isaac, voy a pedir que des la palabra a Martín Díaz Vieira.
Ya la tiene, doctora. Cuando pueda.
Gracias.
Ok, ¿se me escucha? Sí.
Sí, se te oye bien, Martín.
Excellent presentation, Professor Sahimi.
Thank you.
My question is the following. If you have seen the option of the multi-point simulation method,
yes,
with cross-correlation simulation of random fields,
yes,
using copulas. Maybe you know that copulas is a more general approach for dependence, for establish dependence in a multivariate setting.
So what is the question? I mean, I didn't get the question.
If you have seen this option.
Yes, of course, yes. I mean, I don't know whether it is a bare option or a worse option, but of course there are many approaches to this problem. For example, the cross-correlation function simulation that we developed, we now combine it with deep learning approaches to make it even more efficient and do larger scale calculation. And cross-correlation function simulation is just one reconstruction method. There are other methods that people do. The advantage that I see in our method is that since it is a cross-correlation function between the sample of data that we take and the entire image or data that we use for reconstruction, it takes into account multi-scale heterogeneity. Whereas when you look at, for example, a two-point correlation function, it is local and it doesn't go far enough in order to honor the heterogeneity in the system. Now, of course, there are other methods of doing it. There is no question about it. But at least in terms of computational efficiency, the method that I described is very efficient.
Thank you.
You're welcome.
¿Hay más preguntas al doctor Sahimi?
Yes. I'm done.
Yeah, it seems there's no more questions at this moment, but you offer that the people can send the questions later by email. So thank you very much, Dr. Sahimi, for your very interesting and very broad explanation of porous media applications and characterization and modeling.
Let me emphasize that I am delighted and honored to be with you and to talk to you. I've had many friends and colleagues in Mexico over the years, and I collaborate with some of them. And I'll be happy to collaborate with anybody who is willing to collaborate with me. It's open. Anybody who wants to collaborate, I'll be happy to collaborate. I love collaboration, and therefore I look forward to anything that you guys may suggest. And as I said, if you have any question about my presentation, please send me an email, moe@usc.edu. and I'll be happy to answer the question. And I thank you again for including me in your conference and in your sessions.
Thank you very much, Dr. Sahimi, and thank you very much for your offer to collaborate with you. And, thank you.
Okay, I wish everybody a good day.
Yeah, I will put your email on the chat of this conference so that people will have it.
Yes, it's moe@usc.edu. It's very easy.
Okay, thank you very much.
Thank you.
You're welcome to stay, but the rest of the conference will be in Spanish.
My children know Spanish very well, but not myself.
Okay.
Thank you.
Okay. So I think that we will maybe, I don't know, Gorgonio, the next, you can start the next session.
Sí, gracias, doctora. De acuerdo al programa original, se tiene una sesión a las 10:30 de Carlos Romano. Sin embargo, nos compartió un mensaje de que por causas de fuerza mayor no va a poder presentar. Bueno, entonces el mensaje para Carlos es que no se preocupe y ojalá y más adelante tenga la oportunidad de podernos compartir los desarrollos que está haciendo en colaboración con el doctor Martín. Entonces, para no alterar el programa, nos veremos a las 10:50, en donde el doctor Martín nos va a presentar un trabajo y ya haremos el anuncio en su momento, ¿ok? Entonces, continuaríamos a las 10:50, por favor.
Ok.
Gracias.
Sí, quiero hacer una pregunta, no sé si me escuchan.
Sí, sí la escuchamos, doctor.
Sí, se está grabando todo. Me imagino que vamos después a subirlo a YouTube, a un canal. ¿Ya se tiene?
Lo desconozco, no sé si aquí me pueda apoyar Isaac o alguien más del comité para que nos comente al respecto.
Sí.
Sí, doctor, lo estamos grabando, pero la doctora Ana Hansen no sé si tenía planeado subirlo exactamente a un canal de YouTube o compartirlo de alguna manera.
Yo creo que es una oportunidad, aprovechando el tiempo vacío, para crear un canal que sea del capítulo, por ejemplo, o de la conferencia. Puede ser solamente de la conferencia, ¿no? Y subir las presentaciones, claro, previa autorización de los autores y todo esto que consideren, ¿no? Porque entonces eso es lo que le da más difusión a este tipo de trabajos, ¿no? En el peor de los casos, compartirlo con los autores las grabaciones, ¿no? De sus conferencias. No sé si está Ana no está por ahí.
Tu micrófono, doctora Ana, está desactivado.
Sí, un momento. Sí que puede, doctora, conectarse.
Sí, sí, nada más que necesitamos a alguien que lo edite, ¿no? Y porque si no va a servir, porque ahorita sale todo un video con todo lo que estamos platicando ahorita, y etcétera, etcétera. Entonces alguien tendría que editarlo y también
es muy largo. Es decir, no recomiendo que graben todo eso continuo. Eso es muy largo.
Sí. Okay.
No, es decir, que paren, guarden. Es decir, en general, eso es como una máxima en computación. Guarda un pedacito, no guardes todo porque vas a perder todo, ¿no? Es decir, si se cae la conexión ahora, a lo mejor puede ser un desastre, ¿no? Y puede pasar. Sí. Entonces sí les recomiendo más bien que guarden tramos, sobre todo, o sesiones, no sé, guarden tramos, ¿no? Sí. Pero editarlo es muy fácil, realmente no es muy difícil, suponiendo que nada más que vamos a cortar, ¿no? Las conferencias, en el peor de los casos que no veo el nombre, tiene Isaac mi puesto, es Isaac, ¿no? Sí. A Isaac yo no sé nada de eso, pero eso es lo que yo he hecho con mis clases, ¿no? Yo imagino que otros son más especialistas que yo, Pero creo que es muy fácil, nada más que con cualquier programa de edición de video que hay libres, multiplataformas, se corta al principio al final, ¡tum! Y ya, se queda un pedazo y así, ¿no? Se cortan los pedazos y se guarda con un nombre, y el canal se puede crear rápidamente. Hay un correo, ¿no? De CMI, ¿no? Del capítulo, ¿verdad? Creo que sí, ¿no? En fin, el canal se crea fácilmente también. Es nada más que unos clics y se crea el canal. Al momento, ya sea del capítulo, ya que es más general, ya sea de esta conferencia. Entonces, nada más que le ponemos RACMI 2021, no sé qué.
Ok,
¿sí?
doctor, yo solamente tenía nociones o sea, de grabación, que tenía que grabar toda la sesión, pero lo que diga la mesa directiva, yo no puedo decidir.
No, está bien. No, yo nada más que me ofrezco para si cualquier cosa ayudarte, pero me imagino que hay muchísima gente, porque eso está muy de moda, digamos que estamos haciendo esto, ¿verdad? Pero está súper de moda todo. La vida está en YouTube, vamos a decir así, ¿no? La vida no ocurre aquí, sino allí, ¿no? Y las directas y todo esto, ¿no? Entonces, ok. Entonces,
pero no sé, perdón, pero no sé si ya preguntaron si si Sahimi e Interpore dan permiso de poner la conferencia, la Kimberley-Clark en
No,
nuestras
por
redes.
eso, no, a cada gente individualmente sí. Eso es lo que yo pensé por ahí. Que debe tocar el permiso para subir su plática. Y digo, al menos que nos las compartan. Porque ustedes están grabando, pero yo no estoy grabando, ¿no? Digamos, mi plática, ¿no? Me refiero. Entonces yo mi plática sí la subo, después de los casos, a mi canal, vamos a decir así, ¿no?
Sí. Me imagino que mi tocayo, Eric Díaz, puede apoyar con esa parte de, ¿cómo se llama? Ir grabando por bloques, ¿no? Como dice Martín, que yo creo que es la estrategia correcta.
Mejor.
Claro, sí, por supuesto.
Okay. Gracias.
Bueno, al respecto nada más, quiero pedirles que alguien más se encargue, porque Eric y yo a las 11 tenemos otra reunión con la UNESCO y nos tenemos que retirar por unas horas.
Entonces, doctora Ana Hansen, ¿grabo cada conferencia como si fuera un bloque?
Sí, mejor.
Ok, yo, disculpa Martín por mi inexperiencia, pero pensaba grabarlo de jalón todo. O sea,
sí.
Qué bueno que se comentó.
Sí. Disculpen por estos pequeños errores de...
No, ¿por qué disculpar? ¿No? Está bien. Más bien lo que hace falta, es decir, lo que estoy diciendo para prever cosas, ¿no? Igual hay otra gente que conoce más, ¿eh?